So, welcome to Biomaterials. What are we going to talk about today? Well, today we're going to talk about the importance of maintaining a proper stoichiometric ratio when you're forming condensation polymers. So the stoichiometric ratio in condensation polymers. So if you remember, we had for condensation polymers, there's some polymers that basically form, for example, we have some body and there's some group A on one side and some group B on the other. I'm not talking about these polymers today. The condensation polymers that I'm talking about today are the ones that have an A and an A and an equal amount of B and B. So the idea is in order for these to polymerize, we need an equal amount of these two types of polymers. We need an equal amount for high molecular weight. We need an equal weight to, an equal amount, an equal molar ratio of these two polymers to get a high molecular weight polymer. And if you remember, there was a formula for m sub n over m1 that that was equal to the following. Sorry about that. It was equal to this 1 plus r over 1 plus r minus 2 rp. And if you remember, P was the degree of polymerization. So as the reaction goes to completion, so as reaction goes to completion, P goes to 1. So that means m sub n over m sub 1 goes to 1 plus r over 1 minus r. So what does this mean? Well, if you looked at this as a function of p, this m sub n over m sub 1 over p. P can essentially go from 0 to 1, and it starts at 1 right here. If you sub in p equals 0, then you get 1 over r over 1 plus r, right? So it starts at 1, and if r equals 1, then we can get this vertical asymptote right here. But if r equals, for example, 1 over 2, which would sort of mean like 1 mole of your AA type for every 2 moles of your BB type. If you sub in r equals 1/2 right here, then m sub n over m sub 1 ends up being just 3, even if we let p go all the way to 1. So m sub n over m sub 1 goes to 3 if you sub in 1/2 right here. So what does this mean? Instead of getting a near infinite molecular weight, i.e. very long chains that we would get for good mechanical properties, it just goes to 3. So we get something that looks like that, 3 right here in this scenario. So what does that mean? Well, that basically means we have essentially a polymer chain that looks like this. We have, our AA, and basically each AA is capped off by 2 BBs, and then everything is sort of just Bs bumping against other Bs that can't really polymerize. So we'd sort of just get this chain of length 3, rather than if we had equal numbers, then all of the chains could eventually link up and form something of near infinite length. So what's the key thing here is, how do we enforce this proper stoichiometric ratio, right? Here, the importance of a proper stoichiometric ratio is clear, and even just having one of these be just a percent bigger than the other means that instead of getting infinite, we suffer huge losses in our achievable molecular weights. So it turns out there are two strategies There are basically two strategies for getting high molecular, for enforcing this proper stoichiometric ratio for getting high molecular weight. So two strategies. So one strategy is to form a salt and then react to polymerize. So if you dust off your notes from the previous lecture, there's one polymer that's formed via condensation. So nylon 6,6, which basically has an NH2, and then 1, 2, 3, 4, 5, 6 carbons, and then another NH2, and this reacts with COOH. So 1, 2, 3, 4, 5, 6 COOH. So the 6 comes from the 6 carbons here and the 6 carbons in this chain. So these react with one another. Well, it turns out that if you just dump these, in water or whatever, they wouldn't necessarily just react spontaneously, but rather this amine group becomes sort of reacts with water, and this acts like a base, i.e., it grabs onto an H plus. So an H plus from the water sort of grabs onto this, and this becomes NH3 plus. So basically, an H plus hitches a ride on here and on here, and lends this to sort of be to get 2 plus to this overall molecule, and these become COO minus. So these become COO minus. So what does this mean? Basically, these don't react immediately to form a covalent bond spontaneously. So spontaneously, not a covalent bond, but rather it forms a salt, right? In the same way that, like, if you had, NaCl, it's not like an Na and a Cl react with one another, but rather it's this like it's this structure of like positive and negative ions that sort of form a crystal. So in the same way that NaCl can come out of water, come out of solution of the water as a salt, this nylon, this hexamethylene diamine and the adipic acid, these can precipitate as a salt. So this can also precipitate as a salt. And what's the key thing here? Basically, if you have a salt, there's no sneaky sodium chloride salt crystals that like somehow snuck in an extra sodium or an extra chlorine, right? It's not like 51% sodium and 49% chlorine. No, it's a 50-50 ratio because it's enforced by how the charges interact with one another. So it turns out that you can basically precipitate nylon as a salt, and basically this means we get a 1-to-1 ratio by the chemistry. So basically, we precipitate it as a salt by the chemistry, and then heat to polymerize. And it turns out that this is basically what's done industrially. You basically create these molecules, create a solution of them together, precipitate out that solution as a salt, and then you basically have this block that has a perfect molar ratio of these two constituents. You polymerize that block together, and you get your and then you get a high molecular weight because you have a proper molar ratio. So this is strategy number one to form a salt. Strategy number two is to use solvents. Sorry, strategy number two is to use solvents but these solvents are basically mutually or sort of immiscible solvents. Use two immiscible solvents, where one of the reactants can only react in or is only soluble in one, and one is react in the other, but it polymerizes at the interface. So what might that look like? Well, imagine I had a beaker, and in this beaker I had two solvents, and let's say it looked like here. So in the bottom, I had water, and in the H2O is your hexamethylene diamine. So your NH 1, 2, 3, 4, 5, 6 NH H. And it turns out that this is soluble only in water. But on top of this water, you put some kind of organic solvent. Right? So some hydrocarbon, something like that, right? And we all know that oil and water don't mix, so the organic solvent will sit up here and doesn't mix with the water, right? So these don't mix in the same way that your oil and water don't mix. But dissolved within this organic solvent is not adipic acid, but an acid chloride. So if you remember, nylon can form not just with COOH, but COCl. COCl. And it turns out that this is only soluble. This is only soluble in this. This is only soluble in this. But at the interface, they can react. And it doesn't matter if we don't have a perfect molar ratio of the two, because they can only react at the interface. We always get more of this diffusing towards the interface to replace what's lost in the reaction, and more of this diffusing to the interface to replace what's lost in the reaction. And it doesn't matter if there's a little bit of extra of the um, carbon compound, or of the carboxylic acid, or sorry, of the acid chloride compound, or of the amine compound. It doesn't matter if there's a little bit of extra one or the other, because they're only reacting at the interface. Both things are basically continually diffusing to the interface to make up to join the growing chain. And it turns out that this is called the nylon hat trick, or the nylon rope trick, because it looks pretty funny when you actually do it in real life. You can have a beaker, you set up these two things, you essentially pour two liquids into a beaker, and then you can basically reach in with a hook. You can reach in with a hook and essentially grab onto solid nylon that forms at the interface, and you basically pull out a rope of nylon, and you can essentially pull that rope sort of from the interface, kind of out of a liquid. So you basically pull it out, and a nylon rope essentially pulls out of two liquids. It turns out that this isn't really used in industry too much. This is more of a cool demo, and I'll link to a video on YouTube of someone doing this in real life. It's pretty neat. You can see them sort of pull nylon out of a beaker, of two things. I don't think they might use slightly different molecules than these two that I've listed here, but again, this is what they do. And basically, by separating the two compounds and allowing them to sort of only react at the interface, then sort of they're resupplied in an equal molar ratio to replace what's lost, and that also can enforce the stoichiometric ratio. And you can get pretty large molecular weight nylon out of this reaction here. All right, so that was just a short lecture this time on how and why it would be important to get a proper stoichiometric ratio when polymerizing these condensation polymers. Thanks for watching, and good luck with your study of biomaterials.